It is my pleasure to welcome Ben Hunt here for the first time, I think. Yeah, finally. Ben is visiting us from Carnegie Mellon University, where he's an associate professor in physics. He got his PhD at Cornell in the group of Seamus Davis, studying the physics of solid helium-4, and then moved into lower dimensions in his postdoc, where he started working on atomically thin materials, graphene, and so forth. In particular, did really beautiful work discovering the Hofstadter butterfly in graphene. That was actually during your postdoc, right, at MIT 2009 to 2014, which he followed with a one-year research scientist position at Columbia University, working with Jim Hone and Corey Dean, also on atomically thin material systems, before moving to Carnegie Mellon in 2015, where he's been ever since. Continuing to do lots of things, playing a part with Scotch tape. So this is more recent work on tungsten ditelluride he'll tell us about today. So Ben, floor is yours.
Thanks a lot, Eric. Thanks for the invite. Had a great time chatting with people. This is my first talk that I've given in 2 years that it was not on a screen. So
oh, you're on somebody's screen.
Somebody's screen. Maybe at least a majority of people in real life. Yeah, so thank you. It's really nice to be here. This is Carnegie Mellon. This is where my office and lab is in this building. This is the University of Pittsburgh. Everybody asked about that, looking down on us from the Cathedral of Learning. Okay, so I'm going to tell you today about a measurement technique that we've developed to be able to measure the separation of charge or the polarization in a bilayer system. Okay, and the bilayer system of interest is WTe2. So, you know, I think everybody is getting saturated with new two-dimensional materials. You've probably heard 100 million talks about this 2D material and that one. I do want to mention before I launch into it why this one is of particular interest. And the main reason is that when you bring it down to a monolayer or a bilayer, there are many, many tunable electronic phases. Okay, so this is a very rich material. It has spin orbit coupling because of the heavy tungsten. It has a very unique broken symmetry states, as I'll tell you about, and it's also very hard to work with. So you can kind of get in a niche there. So just to give you a sense of it, so in the monolayer, it becomes a topological insulator. Okay, and my group's foray into this has just basically been in scanning tunneling microscopy. So we studied the edge states of this two-dimensional topological insulator. If you now say take it and increase the electronic density in it, it turns from a topological insulator into a superconductor. And this is a very rare example of being able to tune, for example, from a superconductor to a topological insulator in a single material. Okay. So we've also gotten on the bandwagon of twisting a little bit. So we made twisted bilayer WTe2 and studied a little bit with STM. And again, because of the symmetries in this material, you don't get these kind of typical C3 symmetric moire patterns that you may have been used to seeing. You can actually, because the sort of hexagonal, or sorry, rectangular symmetry of the unit cell, the moire pattern ends up being these chains. And so you can do some possibly one-dimensional physics in twisted bilayer WTe2. Okay. So this is some other work that has been happening in my group and others, but today what I want to tell you about is bilayer WTe2. And bilayer WTe2, as far as we know, doesn't have any of these things. You just add one more layer and it becomes a very different type of material. In particular, it becomes a ferroelectric material. Okay. I have to admit, when I got into this, I knew nothing about ferroelectricity. I know only a little bit more now. So that is why I would like to tell you for the next couple slides a little bit about ferroelectricity. Jeez. What's going on here? I'd like to tell you just a little, give you a little bit of a gentle introduction to ferroelectricity. Okay, so ferroelectricity is basically a symmetry broken phase that's characterized by a macroscopic polarization, a macroscopic separation of charge. And you can switch it with an external electric field. Okay, so if this type of diagram, polarization versus electric field, looks familiar, it's because there's a lot of analogous things in ferromagnetism, which you may be more used to. For example, there's a remnant polarization in this bistable configuration over here, and there's sort of a coercive field as well. So all the analogous things from ferromagnetism. Okay. What do you need to get ferroelectricity in a crystal? The sine qua non is the broken inversion symmetry. Okay, you must have this. A broken inversion symmetry is synonymous with having a polar crystal, which is, geez, something wrong here. Which is shown here. Okay, so this is a perovskite, which is where ferroelectricity usually lives in insulators. And here you can see, for example, in the polar crystal, there's broken inversion symmetry because the central titanium atom here is a little bit out of plane above and a little bit out of plane below. Okay, and so a lot of ferroelectrics are in these perovskite materials. Broken inversion symmetry is not the only thing you need, though, right? You also need long-range order of this spontaneous polarization. So just to give the connection to two-dimensional materials, in graphene, clearly you have inversion symmetry, right? The A and B sublattices are the same. If you go to a material like boron nitride, right, where you now have boron and nitrogen on the two sublattices, you definitely have a polar crystal here. But the polarization is not unique because, for example, you can just rotate by 120 degrees, right? And then you have a different polarization axis. Okay, so the polarization is not unique here, and you don't get the long-range order that's necessary for ferroelectricity. And then finally, you need something like a couple of energy minima so that you can have this bistable behavior and you can have this hysteretic behavior and therefore the switching. Okay. Good. So why is it interesting? It's interesting to a lot of people for a lot of reasons. To me, it's interesting from this physicist's point of view. It's a very simple system in which you can study, for example, phase transitions, quantum phase transitions. So in strontium titanate, for example, or related oxides, you can go from a paraelectric material to a ferroelectric material. And Chang and I were discussing today some very interesting ideas about using NV centers to sense this type of quantum phase transition. Polarization is also directly related to topological properties of materials, so Berry phase properties of materials. You can see in this recent book from David Vanderbilt, the modern theory of polarization is kind of built around Berry phases. Electric polarization is the first word in the subtitle of this paper. So you can use topological properties to learn about polarization and vice versa, okay, in these materials. Certainly relevant for being able to have magnetoelectric materials, right, where you can interchange spins and charge in a way, multi-Ferroelectric materials. And nowadays, there's actually a lot of new stuff to discover and to understand about ferroelectricity. So for example, just last year, it was discovered that in plain old Bernal bilayer graphene also displays ferroelectricity. So they're keeping surprises from graphene. And then finally, what the subject of this talk is ferroelectricity in metals. Okay, most of the things that are used in industry that are ferroelectrics are insulators. Okay, so I'm gonna tell you today about a sort of interesting system in which you have simultaneous ferroelectricity, but also metallicity, so metallic Bilayer. And that's basically those three ferroelectric criteria I showed you before, plus the ability to actually conduct electricity. Okay, so where are they? Where are these ferroelectric metals? If you just sort of think about it for a couple minutes, polarization in a metal is not expected because if you have an internal electric field due to charge separation or something, it's naturally going to be screened out by mobile charges, right? And moreover, it wouldn't be switchable. You would not be able to switch it due to the screening of the electric fields as well, right? So what do you need? You need a system with crystal symmetries that prevent the screening of this polarization, that sort of lock it in. And you need really ultra thin things to enable the electric field to penetrate and actually be able to switch the polarization. So naturally, this is going to happen in two-dimensional materials. Okay. Good. So let me just give you two slides about the sort of history of ferroelectricity in two-dimensional materials in sort of reverse order. Okay. So the most recent things that have been discovered have actually been in the insulator boron nitride. So in this now very popular method of taking things and twisting them. So people have basically taken boron nitride and figured out that if you make twisted bilayer boron nitride, you break the inversion symmetry that is inherent in the naturally grown crystal, and you can get ferroelectricity in that material. Okay, so this is a picture using something called piezoelectric force microscopy of the ferroelectric domains in twisted bilayer boron nitride. And this has also been done, by the way, in all of the transition metal dichalcogenides, so MOWSE2, all of them. And this has all been done recently in Pablo Herrera's group at MIT. Okay, so you can get ferroelectricity intentionally from breaking inversion symmetry by stacking crystals in certain ways. But what about the intrinsic ferroelectricity in certain 2D materials? And I had a nice discussion today earlier about all of these materials recently that you've worked on. So there's the copper indium thiophosphate, indium selenide, et cetera, et cetera, et cetera. And so far, all of these have been studied by this technique where this piezo force microscopic technique, where you essentially have to measure the domains of ferroelectricity. And so the thing that I'm going to tell you about right now, which is this WTe2, the reason why it's unique is that in 2018, it was discovered that you could basically study it using transport measurements, again, because it's a metallic material. So this sort of opens up new ways of studying ferroelectricity, not the sort of typical way using force microscopy.
Are you saying the other ones are not conductive?
Yes, these are not conductive.
So
Yeah.
molybdenum is not.
Well, sorry, molybdenum actually fits in the same category as WTe2. It's just that it had not been, as of 2018, studied in this way, but it doesn't mean that it cannot be. Yeah. Okay, so this material WTe2, as I mentioned before, lacks the C3 symmetry of the typical transition metal dichalcogenides that you may have heard of before. This is what the unit cell basically looks like. Well, it's sort of small there, right? And this is what it looks like from side view. And the reason why it has this C2 symmetry instead of C3 symmetry is that there's this kind of staggering of the transition metal atoms, excuse me, of the chalcogens out of plane. Okay, so if you're used to sort of thinking about the electronic structure of a material as having some hexagonal Brillouin zone, put that out of your mind. The Brillouin zone of this material looks like that instead, okay? And then these 2 points, the Q and Q prime points, are the minima of the valleys, so-called. Okay.
So it undergoes one of these structural phase transitions.
That's right.
So, yeah, and that happens as
At much higher temperatures, yeah. Yeah.
Compared to like MOTe2? Or?
Oh, that I'm not sure. I'm not sure what
temperature does the transition have?
I think well above room temperature.
Oh,
yeah. So this ferroelectricity persists at least up to 300 Kelvin. Yes.
So is this two structure issue?
These are two slightly different structures. This is the so-called 1T prime structure and the TD structure.
Which one lower temperature? What is the phase transition? If I cool down it, or
I'm not entirely sure. I think that they're just two minima in the sort of energy landscape, so it can enter either of these two phases. Yeah.
you see CDW?
No, as far as I know, no. Yeah, I haven't seen any reports of CDWs in this material. This also depends a lot on the substrate and other the devices in which the differences are quite subtle, I think, and it's actually not clear from our work which of these two structures it is. We can't probe that. So this is the monolayer of the material. The bilayer of the material is basically has broken mirror symmetry, but if you take one of these layers and you flip it upside down, you create the bilayer. Okay. And so if you mirror the bilayer structure, what you have now is a polarization that points either in this direction, or if you take the mirror image of it, a polarization that points in the opposite direction. Okay, so it has broken mirror symmetry, and that corresponds to the two polarization states. Okay, if you like, rather than trying to visualize the symmetries, if you like to just look at where the electrons are in the system, on the left here is a sort of artificial structure that has inversion symmetry. This is the real structure which has broken inversion symmetry. Okay, the real bilayer. And what you can see if you focus in here is that you can easily draw a center of inversion here. Right, the colors basically correspond to some isosurface of electron density. Okay, so in the real structure over here, there's no center of inversion. You can kind of see that there's an overall deficiency of electrons up here and an overall accumulation of electrons down here, and it actually corresponds to some natural transfer of electrons from the top layer to the bottom layer. Okay, so this is sort of at the root of what the polarization is. You have more charge on average on the bottom than on the top. Okay, I wanted to describe, before going into our results, I wanted to describe the experiment that sort of kicked this all off in 2018. And it's not to say it's a very large field. There's really only been 2 or 3 experiments on this material. But this comes from David Cobden's group at the University of Washington. And the measurement that he did was to sandwich WTe2 between a top gate and a back gate. And to just measure the conductivity of the WTe2. And what he sees is as he changes the out of plane electric field, right, as he sweeps one way and then sweeps back, he sees this bistability, right? So he sees this hysteretic behavior. So the WTe2 shows conductance shows switching with perpendicular electric field, which is what you need, one of the ingredients that you need for ferroelectricity. Now, that was one of his experiments, but the sort of, I would say the more important experiment was that he managed to prove that it was in fact an out of plane polarization. Okay, we sort of knew that it was because of the mirror symmetry, but this was the proof that it was an out of plane polarization. So what he did here was he placed a graphene sensor, namely he studied a graphene layer above the WTe2 here. And basically what happened was, based on the 2 polarization states in the WTe2, it would basically change the density in the graphene and therefore to change the conductivity of the graphene. Okay, so just to summarize that, if you sort of imagine from bottom to top what the electrostatic potential has to look like if the bottom gate here and the top gate are grounded and there's a finite polarization, finite electric field in the WTe2 layer, the electrostatic potential will switch. It will sort of follow one profile for one polarization and a different profile for another polarization. Okay, so he can basically do 2 experiments, one in which he puts the WTe2 at ground potential and sweeps the back gate, right? And in fact, it doesn't have much effect on the graphene up here because essentially the field lines terminate in the WTe2. But in this middle regime, he can change the back gate and see the bistability as reflected in the graphene. Okay, and then what he can do is forget about the back gate, use the WTe2 as a gate, and change the conductance of graphene, and he can equate these 2 things. Okay, these 2 effects on the graphene. And the reason why I'm telling you this in detail is that this is quite a complicated experiment, but he can get some quantitative number for what the polarization is in this material by essentially relating this electrostatic model to what he measures in the graphene. Okay, so he has a pseudo quantitative measurement of what the polarization is in the material. And the number down here is 10 to the 4 electrons per centimeter. Okay. If that doesn't mean anything to you, that's okay. Let me just try to tell you what that means. So if you think of an electronic, a dipole, a plus and minus charge separated by d, then it has a dipole moment that's E times d, right? Which would be in electron centimeters or Coulomb centimeters, if you like. Those are the units, okay? So the number that is quoted up here, 10 to the 4 electrons per centimeter, is really equivalent to taking these two dipoles like this, essentially transferring a certain amount of charge from one layer of this bilayer to the other layer, okay? So this number is really an areal polarization density. It's a number of dipoles times the number of electrons per unit area, okay? So so if you see these units, electrons per centimeter, that's what it means. It's an areal polarization density, okay? So Professor Cobden has determined this number from these clever experiments with graphene, and he can prove that the polarization is out of plane, which is great, and he can estimate the magnitude of P based on this electrostatic model that I told you. But what the measurement cannot do is a precise measurement of the polarization, which is what I want to tell you about next. And maybe more importantly, and especially for this semi-metallic behavior, it's not easy to explore the density dependence. Like if I can change the electron density in this ferroelectric semi-metal, what effect does that have on the polarization? So that tells you things like the role of screening and what the wave functions are really doing in the WTe2, okay? And so that is our goal, and that was our goal when we started this project, is to sort of try to achieve these things.
Can I ask, just technologically,
Yeah.
10 to the 4, is that big, small?
It's small. It's small. It's I'm glossing over that, but it's like 2 orders of magnitude smaller than barium titanate or one of these useful ferroelectrics. Yeah. Okay, so our measurement, the thing that we know how to do in my lab is make capacitance measurements, and make capacitance measurements of very, very small objects. Okay. So this is the structure of the device that we made. There's a bilayer of WTe2 sandwiched between a top gate and a back gate. And the measurement we make is capacitance. So what we do is we apply a small AC signal to one of the gates, and we measure the change in the charge on the 2 plates or on the 2 layers of this bilayer simultaneously, okay? So if you like, the capacitance that we measure, the top capacitance or the back gate capacitance, is the change in the total charge on this plate given a change on the top or the bottom plate, okay? This is a dual gated measurement, which means that we can either measure the top or back capacitance, okay? And we can change the top voltage and the back voltage to simultaneously change the density and electric field in the material, okay? So maybe just a couple details for people who care about such things. We had to do this entirely in a glove box because the WTe2 is extremely air sensitive. And so we used a technique called via contact method, where you start off with a boron nitride with contacts embedded in it. And then we can pick up the WTe2 and place it on something with a back gate, and then we can finish the fabrication afterwards, okay? And then another technical detail of this measurement is that the charge sensing is done with a little on-chip high electron mobility transistor, which is placed right next to the object that we're trying to measure to minimize capacitances, et cetera. So this is a technique that was essentially invented by Ray Ashuri at MIT, which I learned there. Okay.
What's the frequency range you're using?
So it's basically audio frequencies, yeah. The hemp will work up to a gigahertz or something, but we're not doing those measurements. Okay, so why do we do a capacitance measurement? What is a capacitance measurement? A capacitance measurement is a thermodynamic measurement, okay? It's actually a measure of the so-called electronic compressibility or the thermodynamic density of states. Those are sort of 2 equivalent ways of saying the same thing, okay? So this is an equation which tells you that if you apply a voltage to a pair of capacitor plates, right, you have to pay a charging energy cost. Which this is really just Q over C, right? But if there's a finite level structure or a finite chemical potential, you also have to pay that cost, Okay, so normally in a capacitor, in a macroscopic capacitor, you only have to pay the electrostatic cost, so Q equals CV, right? In a capacitor that's made out of something with a low density of states, like graphene or a carbon nanotube or something that has a low density of states, you also have to pay this extra energy cost. And what that results in is that the measured capacitance is actually a series of the geometric capacitance, like epsilon A over D, plus something that's proportional to dN by d mu. And that's known as the electronic compressibility. Okay, so you can think of two capacitors in series. One is the geometric capacitance and one is the so-called quantum capacitance. Okay. Yes, and then this quantum capacitance is the same thing within a constant as the thermodynamic density of states or the compressibility. Okay, so how do you think about that? You think about that in the following way. When you have a small capacitor in series with something, it dominates, right? So when the density of states of a material is very small, like for example, in two-dimensional materials or in the quantum Hall regime or something like that, you can see a large change in the measured capacitance as you change something like the magnetic field or the voltage or something like that, right? So out here in this kind of toy measurement, out here where the capacitance is high, that means you're measuring the geometric capacitance and the density of states is high, and it looks like the plate that you're trying to measure is metallic, right? But now the density of states gets low. For example, if you go in a gap of a semiconductor, a two-dimensional semiconductor, and then the capacitance dips down and you measure something that's proportional to the quantum capacitance. Okay, so it's a good sensor of things like gaps or low densities of states, and it has been used to do those types of measurements. Okay, so in monolayer graphene, this is what it looks like as you change the gate voltage or the density. Some of you may know that the chemical potential is proportional to the square root of the density in graphene. And so when you measure the capacitance, which is has a component that's dN by d mu, you see this root n dependence as you go to the Dirac point. Okay. So what does it look like in this material, bilayer WTe2? It has some similarities. There's a very low density of states near the charge neutrality point, so that if you sweep the density, you can also see this dip. You see an electron-hole asymmetry here, and you can also see that actually the size of this dip changes as you change the electric field out of plane. Okay. And so that basically reflects the fact that you can, because you have mu here, you can measure a delta mu, which is a gap, and then that gap will basically increase as you put a large electric field on the material. Okay. So this is sort of what the bare figure 1 measurement looks like.
Can you go to the previous slide?
Sure.
Where is that unsymmetric feature coming from?
Do you mean why it goes up here, or why is it just asymmetric?
Yeah, why is asymmetric?
Oh, because there's strong electron hole asymmetry in the band structure.
Wow.
Yeah, I can show you in a little bit. Okay, so this is the key slide of our measurement. So when we actually measure the capacitance, in this case, the top gate capacitance, it shows switching with the electric field. Okay, so if I take a density and electric field sweep and measure the capacitance, that's the color scale. If I sweep to the right, I get this curve, this color plot. If I sweep to the left, I get this one. And you can see maybe that there's a difference if you go forward and backwards. Okay, so the way that we do that, of course, is we just subtract this one from this one. Okay, so this is what it looks like in one direction, and this is what it looks like when it goes back in the other direction. And indeed, there's a region where there's a large difference between forward and backward sweeps. That's the switching, the switching signature in the capacitance. Okay. So if you make now a plot of what the forward and backwards difference is as a function of density now of the number of carriers in the layer, you can see this type of plot. So this is a line cut of this type of plot. Okay, and the thing that we can do that is not possible in the transport measurements is we can now measure what the dependence of this switching, this polarization is on the number of carriers in the system. Okay, so what you can see is that the difference in top and bottom goes away at relatively large hole densities, and it goes away at relatively high electron densities. And somewhere in the middle, you have very large, you have a largish polarization of the material that has a fairly strong electron hole broken symmetry character to it. Okay.
It looks like there's some discontinuity on the hole side in the first set of plots on the left. There's like
you mean these two?
like there's like that vertical feature only on the negative densities. Yeah, that. Right.
This thing, oh, it's just, so this is the thing that marks this boundary. Okay, so if you can only see it on the negative side, that's only because the visibility is not great there. It's definitely there on the positive side, because that is the thing that defines the polarization switching there.
I kind of see it now.
Yeah. So I guess I was just showing you the raw data, and this is what we really care about, which is the difference between the forward and backward sweeps. Okay. The question now is, what does this jump in, or what does this difference in forward and backward sweeps in the capacitance versus the density tell us about the nature of the polarization in this material? Okay, and to do that, we're going to need a special model of how to understand the capacitance measurements in terms of where the charges are in the bilayer. Okay, so these slides are not meant to necessarily be 100% understandable, but I want to give you a flavor of what of how to connect capacitance to, for example, these quantities and how it can be relatively complicated sometimes. So if you have a system like a bilayer system in which you have a top gate and a back gate plus two layers, the key thing is that actually the chemical potentials and the densities can be different on the two layers. Okay, and in particular, if you have two quantities like the two chemical potentials and the two densities on the two layers, the compressibility really has to be written as a tensor. Okay, so this new 1,1, for example, is how the charge changes on the top layer versus the chemical potential on the top layer, and then the off-diagonal terms are something like how the density changes on the top layer if the chemical potential changes on the bottom layer. Okay, so it can be quite a complicated expression to be able to derive the compressibility in this system. Fortunately for us, and this is a self-consistent calculation, the compressibilities on the individual layers are much greater than the off-diagonal ones. Okay, so lo and behold, we can actually just take these quantities, the individual compressibilities on the two layers, okay, so that you can sort of treat them as being independent in that sense. Okay, and then if you do that, then the capacitance can just be written in terms of, so for example, if I'm measuring the top gate capacitance, it's really just something that is the geometric capacitance, epsilon A over D, right? Which is corrected by something that's the ratio of the geometric capacitance to the quantum capacitance. Okay, so again, when the quantum capacitance gets very small, right, this term gets very large, and then you get a significant deviation from what you would measure just from the geometric capacitance of the material. Okay, so that's the first thing. And this is a point that is some people have some trouble appreciating sometimes, which is that even if I ground these two together, okay, you can still have different densities on the two layers. Okay, and that's because there's a chemical potential drop as you go from a layer out to a contact, through a contact and back to the layer. Okay, so it's important to think about, if you want to understand these things, that you really can have a bilayer system in which you have different amounts of charge on the two layers, even though they're connected together at ground potential outside of that circuit. Okay. Okay. So the compressibilities in each of the layers and the measured capacitance, right? That's basically what we're getting from this. Okay. That's the first ingredient for understanding how to connect the capacitance in this to the polarization that we're measuring. Okay. And then the other thing, of course, is that we have these different quantities, but they're different in the two polarization states, of course, right? If you have polarization pointing this way or polarization pointing this way, then now we have two sets of quantities.
Good. The second ingredient is now if we can measure the layer specific compressibilities, right, how can we connect them to real physics? How can we connect them to the band structure of WTe2? Okay, so this is a little bit more for people that know a little bit more about this particular area of physics, but I wanted to mention it anyway. So in more familiar materials to some of you, such as these WSC2 or MOS2, there's the spin orbit coupling basically forces the spin polarization to be opposite in each of the two valleys of this material, right? If I now add another layer and it's weakly coupled, there's a spin layer valley coupling, which means that if I tell you what valley and what layer you're on, I can tell you what spin polarization you have, okay? So there's sort of or maybe put another way, if I tell you what spin and what layer you're on, I can tell you what valley you're in. So there's an intimate coupling due to spin orbit coupling of layers and valleys in this material. Okay. In WTe2, there's sort of a similar effect where if I tell you what valley you're in, I can tell you also what layer you're in. Okay. And so it's really the spin orbit coupling in the band structure that allows you to have these layer polarized wave functions in the material. Okay.
So that's interesting because that's very different from the reason the same thing happens in bilayer graphene.
In bilayer graphene,
no spin orbit coupling required in that case.
Yeah.
But you get this valley layer identification.
Your
Corresponds.
Yeah. Do you mean in the quantum Hall regime, or you just mean in?
Well, I mean, I just
In
at
free
low
space.
energies in general, I thought, but yeah, sure, like in the
quantum Hall.
yeah. N equals 0.
Yeah, that's true. I mean, certainly you get spin and valley textures and stuff in the quantum Hall regime in graphene, but there the bands have become very flat, right? And so the interactions have become kind of important. This is for a slight, yeah, as you pointed out, it's for a very different reason, right? It's basically due to spin orbit coupling. So anyway, if you basically look at our calculation of what the bands look like, you can see that if I just put the Fermi level here, okay, say at 0, you have a sort of unit probability of being in one layer, okay? So due to the spin orbit coupling, you have a strong layer character to the wave functions in this system that depends a lot on well, what the Fermi level is. Yes.
So is it gapped or no gap?
Um,
It's like have a gap.
Yeah, I mean, it's pretty small, right? If you, so you're right. There's certainly a gap here, but I can't really see it. I think there may or may not be a few millivolt gap, indirect gap here, due to this valley and this valley. Yeah. Okay. So basically, we can take this so-called tilted Dirac cone model of bilayer WTe2. Sorry, I'm really sorry that this is very slow. I don't know why the slides don't catch up with me. We can take this model, which is it's just a phenomenological model. It's a K.P model, so-called, and we can derive basically all of the quantities that we need to make a theoretical prediction of what the capacitance is going to be. So, for example, we can use that K.P model to predict what the compressibilities are in each layer, nu11 and nu22, in each of the polarization states. Okay, and then we can compute the capacitance from those quantities via equations like this. Okay. So that tells us from our model how we can calculate the capacitances. Okay, and so this is what the measurement looks like, and this is basically what our theory looks like. And I don't put the units here, but they're reasonable. Okay, so there's a fairly good agreement, I guess, between what we're measuring and our band structure model for the capacitance. It's not perfect. Certainly there are some features that are not reproduced, at least in this regime, right? So you can see some kind of curvature here that it has slightly opposite curvature there. Okay, so an okay model, I would say, for the capacitance measurements. But where it's really powerful, it turns out, is if we don't worry too much about the background capacitance, this sort of linear polarization, and we just focus in on the ferroelectric regime, okay, where there's a switchable capacitance. Okay, so just to remind you, what we're after is we're trying to. This is the difference between the forward and backwards capacitances as a function of the density. Okay, so there. Let me just spend one slide with a lot of equations, and then we will move on from that. So what it turns out that that the polarization is related to the integration of something called the dipole compressibility, and this is actually not too hard to understand. Okay, so the polarization is going to be the difference between the charge density on the top layer and on the bottom layer. So say N1 minus N2. Okay. What happens to that difference as we change the overall N0, the overall density in here, is something called the dipole compressibility. And this is something that we can measure directly in the capacitance. Okay. So maybe it's not surprising that the total polarization that you get in the system, that's this delta P here, is what happens when you take this dipole compressibility and you integrate it over the density. Okay, so it's effectively taking this measurement and doing an integration of it within some factors. Okay. Okay, so if you complete this, you might guess that if you are interested in N1 minus N2, that might mean that you have to measure both the top capacitance and the back capacitance. Okay, and indeed, if you work through the math, it looks like this term that you would need to get the polarization does indeed depend on the difference between the top and back gate capacitances. Okay, that's maybe problematic, but our Hamiltonian is actually symmetric under inversion and under a mirror operation, and also switching the direction of the electric field. Okay, so we can actually use our data to infer what this nu 2 is based on what nu 1 is. Okay, and therefore that means that we don't have to measure the back gate capacitance. We can actually get a result just from measuring the top gate capacitance. Okay, and this is the punchline, which is that the polarization is equal to the difference in forward and back capacitances integrated over the density. Okay, so we sort of knew this from the beginning, right? Or which is that the polarization is going to be 0 at large densities, and it's going to be sort of maximum in the middle. And so that tells you that basically that has to be an integration, right? That it's the polarization is going to be maximum when the system is full of holes or full of electrons, right? At charge neutrality here. Okay, so integrating this curve indeed gives us something that's proportional to the integral of delta C, and the numerical factor out in front is the details that I'm not going to share with you. But just remember that that this is what the polarization versus density looks like. Okay, and what you can see is something quite striking, which is that there's a large electron hole asymmetry in the polarization. Okay, so our experiment, this is what the bare data look like. This is what the inferred polarization looks like based on basic considerations. Okay, and based on the K.P model, we can match up theory quite well with the experiment. And I was quite thrilled when my postdoc showed me this, because it's very good agreement, even numerical agreement with the experiment, with granted some input parameters like geometries and dielectric constants and stuff like that, but it is a very good agreement. Okay, and this is we are not able to go out to these large densities in the experiment, but here you can see, at least in the theory, what we would expect to happen out here at large densities, which is that it goes away. And actually, a kind of remarkable thing is that on the electron side, it doesn't go away very quickly. Okay, so it actually, the polarization persists to relatively high densities in this material. Okay. numerics. So Eric asked about numerics. So if you calculate, so this allows us, as I was mentioning before, to put a very precise measurement of what the polarization is. And so this agrees pretty well with David Cobden's estimate, but I think that this is a more accurate measurement of that. And just to give you a little comparison compared to those other systems, bilayer boron nitride is significantly smaller, but it's sort of comparable in some ways to the say twisted transition metal dichalcogenide artificial Mare superlattice ferroelectrics. But unfortunately, it's 2 orders of magnitude smaller than useful ferroelectrics.
So like you're here, you expect the polarization to vanish at large densities because of screening, basically, right?
Essentially, yes, that's right.
But so many electrons, and they eventually have to go to the other layer.
Yeah.
Why? So how do I think about the asymmetry? Like, why would that happen? It seems
Good. So no, that's great. So it basically comes from the asymmetry in the band structure. So spin orbit coupling gives you quite a large asymmetry. And so the picture that I like, and I hope it's right, is that this is really a derivative. So the compressibility is kind of a derivative of the band structure, because the capacitance is kind of a derivative of the band structure, right? And so basically, if you have a large asymmetry in the band structure, so that you have like something that's very, very layer polarized. So, all of the wave functions, say, reside on this layer rather than on the purple layer. So if you start with no polarization and you have a very layer polarized thing, you start to fill it up. And so you get a very rapid rise in the polarization. Right? And so this is now a charge neutrality here. And now if you go to the electron bands and they're much more symmetric, right? Now you start to fill them up and some screening happens, but it's not entirely, it doesn't entirely cancel out the layer polarization that is coming from the whole bands. So it's sort of a cumulative effect, right? I mean, you can't just go to this point and guess what the layer polarization is. You sort of have to know what happened beforehand. Okay, so that's why it looks like this. Is the layer bands are much more polarized on the whole side, and so you get a rapid change in the polarization. And then there's sort of it's not that there's poor screening, it's just that there's sort of equivalent screening. Like you put one hole in, or one electron in one band, and at the same energy, you have to put the next one in basically the other layer. Sorry, I should say in one layer and the other layer. So that's at least my picture for the electron hole asymmetry. Okay, yeah, and I guess that's the punchline, which is that there's very good agreement between our experiment and the K.P, and it looks like at large hole densities, it's basically just a screened polar metal, but at large electron densities, you basically have this sort of sustained ferroelectric and doped metal for a relatively large density. Yeah. Okay. Maybe I'll just finish off with something. Maybe a lot of you have been wondering how this actually happens, right? So I told you about the layer polarization and the magnitude and stuff. How does it actually switch? So one thing about this structure is that the mirror symmetry the lack of mirror symmetry that produces the out of plane polarization is actually equivalent to a lattice translation by something like 1/10 of the lattice constant. So an extraordinarily small translation of the lattice, but it does reproduce the polarization, right? It does reproduce the crystal structure of the mirror operation. Okay, so it is thought that the ferroelectricity comes from basically the entire top layer sliding a fraction of a unit cell relative to the bottom layer.
You get domains.
Pardon?
You get domains.
No, apparently not. Yeah. So I actually, that's an open question. We don't know, right? We're not sure. I think that this energetic process is actually probably not as large as it seems, right? You can sort of think about a whole layer moving relative to another one, but I don't think that energy cost is so large that it would be necessary to form domains, for example. So yeah, it looks, I think as far as we know, it looks like basically a sort of single domain object, right? So
Can you tell from the sharpness of the switching?
well, yes, that's true. I mean, it doesn't look perfect sometimes. There are maybe, but it's not exactly like in a sort of magnetization measurement where you can definitely tell like a number of steps when you go through the translation. It looks very clean, I think. Yeah. And there are some numerical simulations to sort of back up this idea from this paper. Okay, let me finish up here. So we basically observed ferroelectric switching in this material bilayer WTe2 using capacitance. And what capacitance allows you to do is to measure layer specific properties, namely the compressibility. So you can say, this is what the compressibility is in this layer. And then using those measurements, you can integrate them and you can deduce what the polarization is in real units of polarization. And our measurements seem to be in pretty good agreement with theory based on K dot P. So that tells you about the sort of the band structure origin, including spin orbit coupling of the layer polarization of the wave functions, which tells you about where the electrons have to go when you change the density, and that tells you about the polarization. So it's sort of a new, I would say a relatively new technique for doing this kind of measurement, especially in 2D metals, it would be relatively easy to extend this idea to say 3 layers, 4 layers, 5 layers. Whereas if you do that with, for example, a transport measurement, the more layers you put on, the more potential for parallel shorting you have, and it will be hard to measure in transport. Right, so let's see. The layer degree is sort of more interesting than ever in 2-dimensional materials. If plain Bernal bilayer graphene is any example, this is a material that's been studied since the beginning of 2D materials, and yet in the last 2 years, people have found that Bernal bilayer graphene is superconducting and it's ferroelectric, and there's a lot of stuff hidden in these. I should say hidden because it hasn't been discovered yet in these few layer materials. So with that, let me just thank my group very much. This work was done primarily by Dr. Sergio de la Brera and by Qingri Cao, a grad student who shared equal authorship on this paper, plus an amazing collaboration with my theorist collaborators, Di Zhao, Wenguan Zhu, and others. And then the crystals come from Xiaochang Yan and David Mandris at Oak Ridge National Lab and University of Tennessee. So that's it. Thank you very much for your attention. Yes, Jesse.
Couple questions.
Sure.
So you did that integral of the polarization or the capacitance at zero out of plane electric field. Do you learn anything about the way the bands change if you do that integral as a function of increasing out of plane field?
Yeah, I don't think.
I guess
So it's a good question. We actually haven't done that. I guess the question would be if I sort of shift this curve over a little bit.
yeah.
Do I see much of a change? My instinct is the answer is no.
Well, yeah, it doesn't look like the behavior changes.
From the data, it doesn't look like it changes that much. And I think from what we've seen from this kind of change in electric field on the band structure, I don't think it changes the bands that much. So yeah.
And so I forget, the polarization goes away as you get a really large electric field?
So yeah, so basically, it's not so much that it goes away. It's just that there's no switching out there. Right? So So basically what happens is that like as you go to very, very large electric fields, right? You know, you can move back and forth in that regime and it doesn't actually change, right?
Okay.
There's no difference between you've already affected the change which is responsible for polarization in one direction.
Nice. Okay.
So you're not measuring it. You're really looking for it would really be like a derivative. And so there's no change, right?
Okay.
As you move it out here.
Pinned it basically.
You basically pinned
I
it.
see.
Yeah. So you're fully polarized in that at that electric field. Yeah.
And then my other question was, has there been any studies of applying pressure to this bilayer and how that would affect the polarization between them? Theory.
There's certainly theory. Yeah. So the colleagues at Oak Ridge that did these calculations, I have too many slides, obviously. Yeah. So my colleagues at Oak Ridge that did these types of calculations, they, at least for our STM paper about twisted bilayer graphene, twisted bilayer WTe2, they basically studied what the bands look like as you reduce the layer separation. And the point of that calculation was to figure out what happens to the edge states, but presumably you would be able to calculate what the sort of layer polarization of the bands were as a function of pressure. I don't know what the answer is. Actually, I don't even have any instinct about what the answer is. Yeah, I don't really know, just because it relies so strongly on a very particular arrangement of the bands. I just don't know what would happen. Yeah. That said, our technique is infinitely applicable under hydrostatic pressure.
Right.
So actually, that would be a very good experiment to do. Thanks for that idea.
Yeah, thanks.
Ask a fundamental question. So you have ferroelectric order.
Yeah.
What's the Curie temperature?
I think it's above room temperature.
This is above room temperature.
Yeah.
Is it sensitive to the carrier density?
So yeah, it's a good question. So in the transport experiments that were done, they could study this up to room temperature, and they still see switching at room temperature. As for the carrier density dependence, as I mentioned, they don't have a direct measurement of the out of plane polarization as a function of density. So yeah, I don't know what the effect is at room temperature of that. I would have to look at the paper and see if in that 2018 Nature paper, if there's a, so you would have to infer what the effect was from the direct transport measurements, because they're not able to do the density dependence. So yeah, I'm not sure. Yeah.
So the secret of having the polarization is have this mirror glide symmetry. Is that right? For the end, you should.
Yes,
How
that's right.
crucial is that? You're saying the glide is 1/10 of the lattice parameter.
That's right.
How crucial is that? If I just take, there's so many examples that has this mirror glide symmetry. If I just take down to bilayer, multilayer, will they all show this, or?
I think so. Yeah. Yeah.
Okay.
It should. Yeah.
So it matter that slide is 1/10 of the lattice parameter, or is half the parameter?
I think so. I have the impression that it does. That if you, okay, so if you have a glide symmetry in a bilayer, right, of a material, and I think that the energetics should be such that you should be able to switch that with an electric field, no matter really what the details of the energetics are. I think just they're sort of all in the same ballpark, or they should be, at least for. Yeah. Give it a shot.
So monolayer is topological insulator you showed at the beginning?
Yeah, it's inversion symmetric.
And then bilayer is the metallic.
Bilayer is metallic. Well, okay, so in the monolayer, there's a 50 millivolt topological gap, which has been studied with ARPAs and STM, et cetera, and transport. And then when you go to bilayer, it basically becomes an indirect semi-metal, right? The electron band comes down, the whole band comes up, and so it's not totally clear to me. So we think that we started with a topological semi-metal, or excuse me, we started with a semi-metal with a very small overlap and applied an electric field and opened up a small gap. I think that that's what some of our measurements indicate. Like these measurements seem to indicate that there's a small gap that we're opening up on the right here.
You're doing the measurement that would see that.
But yeah, it's small, right? It's pretty hard to measure gaps that are of the order of a few millivolts. That's actually why the capacitance technique has become useful for things like fractional quantum Hall states. Sometimes hard to see. It's certainly hard to measure millivolt gaps using transport if you want to do some sort of activation, right? But here you can sit at a fixed temperature and just measure the capacitance and therefore the compressibility, and you can deduce what the size of a millivolt gap. So it's small, very small.
So how are you getting the gap value? Is it from the capacitance value or is it from the width of that feature?
It's yeah, so it's basically like if you have you're basically look for you integrate it again, right? So you have something like d mu by dn, right? And if you integrate that over density, then that will give you a step in the chemical potential. Okay, and that step direct is the gap, because that's the change in chemical potential. If you don't change the density, it's basically going from the top of one band to another. So you do need some. You need to know all of the things like the geometric capacitance, and it helps if your capacitance measurement really goes to zero sometimes. But in any case, you can get some something with some error bars, and it works really well in the quantum Hall regime, where you really do have hard gaps and stuff like that. So this is sort of an application of this to a new situation. Yeah, cool.
So you're measuring the layer resolve carrier density of these measurements, right?
Mm-hmm.
You made a comment at some point that you don't need to measure in use of the backgate capacitance though.
Yes. Yeah.
Does it mean you're not making one of these fancy measurements where you're sending two signals to the top and the bottom gate, and you need two HEMPs to, like what was done in the bilayer paper you did with Andrea?
Yeah, we're not doing that. Yeah, we're not doing
Okay.
that. Yeah, that's all we're doing is essentially using the backgate to as another parameter to be able to change the density in the electric field. All we're doing in this measurement is putting an AC signal in the top and measuring the change in the charge on the two layers with the HEMT. The one that you were referring to, where we don't need to do that. Although, I mean, that would be the right measurement. It's just much harder.
Yeah, it's a much easier setup.
Yeah, it's just much harder to do that.
Okay. Well, thank Ben again. Very interesting.